Okay, so I'm going to do a quick version of what's required for engineering mechanics for chapter 2. Now, obviously these things require lots of videos to cover, so things like forces, apply mathematical solutions to solve products, that requires several videos, which we've gone through separately. What I'm going to do is just clear up and make sure that I've addressed everything in the syllabus. So the first thing is they talk about nature and types of forces. So I can't remember what page, but Copeland has somewhere in his textbook, he talks about concurrent forces. The Metcalfe book also talks about this. So I like to say that a force is a push, pull, or twist. That's what I like to say, that's my definition. But a lot of people, when I ask them, they say force equals mass times acceleration. What they mean when they say nature and type of forces is they're talking about, if I have these three forces, if I have a beam that looks like this, right? And I have A, B, C, and then I have a force R, the reaction that's holding that crazy seesaw up. So maybe we have two little kids and one big kid here. Though that kid here is far enough away. So in this case here, we have all the forces are parallel, and all the forces exist in the same 2D plane. I could theoretically find a piece of paper or something, I could slice it. It doesn't need to be vertical, it doesn't need to be horizontal. It's just a plane that exists somewhere, that is, it all fits in one 2D plane. So we call that parallel and coplanar. The next one we're going to look at is perpendicular and coplanar. So if I had this beam, we looked at this earlier, if we had, if I have a beam like this, it's balancing, in that case, we'd have to have three forces, and these three forces, if I've got three forces, these three forces, they're all going to meet up at the same spot. I'm not drawing a great line here. So typically what we like to do is we like to show these in red. So let's say I don't know this particular angle. Right, this is the three-force rule. Right, what I would do is I'd find where these three, that looks pretty good, I'm happy with that. So if these two meet up here, that's the concurrent, because there's only three forces in this diagram, we know that if there's three forces, they must be either all parallel or all concurrent. If there's three forces in equilibrium, that's a rule. So what I can do is I can draw from here, from this point to the point of concurrency, and I can say that my reaction has to be going there. So if I have A, B, and R. So here, in this case, we have forces that are coplanar and parallel. Here we have forces that are coplanar and concurrent. There's another one as well. We can have lines that are collinear. So the example people typically use is if they're talking about things like headwinds. So if you're flying a plane to Perth, let's just, for simplify, we'll say there's there's the force of the engine, and then there's the force of the tailwind. That's going to let you fly to Perth faster, but then when you try to come home, you've got the force of the engines again, and now you've got headwinds, and that's going to mean that you're going to be slower. So here, the resultant of these two collinear forces, these two add and these two, this one subtracts. So depending if they're in exactly the same line, by definition they're always coplanar. They're actually even more than coplanar. But collinear means that they're directly in the same line. We just add them together. So to be honest, I often tend to forget collinear, but I did, it's worth mentioning. Okay, the next one we're going to talk about is non-coplanar forces. Now, it's worth mentioning that in the HSC, you can't really ask questions about non-coplanar forces. We only ask about things in 2D space, we don't ask about things in 3D space. So we're going to look at 3D space, and what does that look like? Well, you can have parallel forces. So if I draw a chair, I feel as though I've already drawn a chair for this class, but couldn't hurt. Maybe it helps to reinforce what's going on. Okay, so it's not really a chair, that looks more like a table. But if I told you I had a force acting down here, I would have four forces reacting to it. here. So if I said that was 1,000 newtons, I would have 250, 250, 250, and presumably there's another leg here. Now, what kind of drawing did I do there?
Three-dimensional.
Okay, it's a pictorial drawing. What kind of... This is unrelated to our topic, but it's definitely related to the test. What kind of drawing did I draw there? It's a pictorial drawing. I'll show you an alternate way I could have drawn it. I could have drawn it like this. Yeah? I could have drawn it like this. What do we call these two different kinds of drawings? Okay, this is something we need to be able to know for the exam. This is something we test on. These ones here, because it's slanted to 45 degrees, this is oblique, this is isometric. You need to be able to recognize that for part of the test. Okay, but so more importantly, what we're looking at here is we have all those forces are all parallel, but they don't exist in one 2D space. They need to be shown in 3D space. We can't depict them in 2D space. Another example of non-collinear forces is if I have a box. Well, the center of the box here, it has a weight acting down the middle of the box. And then, if I have 4 cables that are pulling this box up, maybe from a crane or something like that, these forces will all be concurrent. Now you might say, well, this force isn't touching these forces, but it can be extended. Actually, that's where I like to use red lines. Some people would say, you're just being pedantic now, Luke. I've decided I'm just being pedantic. There you go. So they're concurrent because they all meet up in the same spot. And this one here, it meets up. I've got it a little bit wrong. Now, that rule about, I said before, the 3-force rule, that if you have 3 forces that are in equilibrium, they must be all parallel or all concurrent. We can see once you have more than 3 forces, that rule doesn't apply anymore. Okay, so they're the nature of forces. The next thing we're going to talk about is we're going to talk about space and free body diagrams. So imagine if I had a bridge. I always seem to draw it as like a sort of stone arch bridge. And down below I've got some dude and he's fishing. I always do the wrong part of it. Okay. He's fishing, and on the top of that there's a truck. Beep, beep. The truck sees something and it tries to stop. Right, so there's a force. The force of that truck is pushing into the, I'm going to draw it that way, actually. The force of this truck is acting downwards into this bridge. Now, that's a very complicated image, so we call that a space diagram. What we like to have instead is we like to simplify that down into what we call a free body diagram. So that's the force of the truck. I'm going to call that Ft for truck. We've got reaction A and reaction B. So this is called a space diagram because it shows space, and this is called a free body diagram, which can be abbreviated to FBD. Okay, resultants and equilibriants. I've spent some time talking about this already, but it doesn't hurt maybe to reinforce it. Oh, the whole point of the free body diagram is it removes unnecessary details. We don't care what the truck looks like. We don't really care what the bridge looks like. We definitely don't care about the guy fishing underneath the bridge. We're just simplifying it down to members and forces. Okay, the next thing that sometimes we do care what the bridge looks like, but not in this particular case. The next thing we're going to talk about is equilibriums and resultants. The example I like to talk about is if there's a girl who's gone hiking and she hikes 1 kilometre north, 1 kilometre east, 1 kilometre south, how far away is she from where she started?
1 kilometre.
1 kilometre. Okay, now vectors have direction. Oh yeah, right? So the resultant of how far she is from where she started, if you were to add up those forces, you would say that she is 1 kilometre east of where she started. Yeah, we okay with that? She's 1 kilometre east of where she started. Now, that's a resultant. An equilibrium is how far would she need to go to get back to her car and drive home? 1 kilometre west. Now, when we're doing this more so this is right here. This is the resultant. Wrong thing. Okay. So the resultant is measured from where you start to where you finish. The equilibrium says, often what we look at, especially the equilibrium of forces, is we look at, most of the time what we're looking at is we're looking at things that are perfectly balanced. We're looking at scales or seesaws or beams that are perfectly balanced. And if that's the case, because civil engineers, I'm not going to explain it, but generally my phrase is, for civil engineers, if it's moving, it's broken. That means that the forces are perfectly balanced. Which means that if you have an unknown force, in this case, if I told you I don't know how far it is back to the car, you can say, well, the equilibrium, the unknown force, is going to be what do we need to get the resultant down to 0? If there's 0 resultant, what force would I need to add in order to get the resultant to 0? That's the equilibrium. I don't really find this distinction very useful. We use equilibriums much more often than we use resultants. But I say that we do need resultants to find the final answers and things. So that's where we chuck in some Pythagoras' theorem at the end and say, oh yeah, that's the resultant force. Anyway, the point, I feel as though equilibriums are conceptually more important, but I wouldn't lose too much sleep over these terminologies. Okay, the transmissibility of forces is the next stop point. And for the transmissibility of forces, what we're saying is that if you have a wheelbarrow, I guess it would work for a wheelbarrow, we're going to instead use a lawnmower. So I've got a lawnmower. If I'm applying a force horizontally of 10 newtons, it doesn't matter if the force is 10 newtons here or 10 newtons there. These are the same. So that's called the transmissibility of forces. I'm going to worry that I'm going to spell this wrong. Okay. Three-force rule. Boy, have we talked about three-force rule, but I'm going to say it again. If you have three forces in equilibrium, they must either be parallel or concurrent. If you know that they're concurrent, you could use a protractor, or if you're really keen, geometry, to find out the angle of an unknown force. Now, very few people use the three-force rule. This year that I'm recording this is the first year that I've ever really tried to push to teach the people a three-force rule. I used to say, look, it's too hard. If you want to do an extension class, I'll do it. But I never really see students use the three-force rule, even when I'm marking outside of the school. So it's not necessary, but this year I've tried to push to explain how to use the three-force method. Once you know how to use the three-force method, the alternative to using the three-force method is using moments. Now, I'm going to come back and explain something else because I'm trying to follow the dot points more or less in order. But if I have a seesaw, and again I've got a force of 14.1 newtons at 45 degrees, and I have another force that's unknown, but I know that it's vertical, that's enough information for me to solve this, as long as I have a drawing that's drawn to scale. So let's say I say this is 1 meter. Right? As long as I know the distances, that should be enough for me to figure out what's going on. So what I can then say is, well, I never used trigonometry, But this time around, rather than using a protractor, we're going to use trigonometry. Now my rule, sorry, I drew those in green, and I never use green. The rule is, so to find the concurrent forces, I don't know this angle. This angle could be anything. But what I do know is I know this angle and I know this angle. And with that knowledge, I can then find this point of concurrency. Because I know that there's three forces on this diagram, and that three forces acting, three forces in equilibrium have to either be parallel or concurrent. Once I know this, I can then find this. Now, how am I going to find that? Well, using trigonometry, if this is 45 degrees and this is 3 meters, well, that means that this side, Sarah, will be how big? How big will this side be? 3 meters, that's right. Because it's a 45-degree triangle. Just a really big 45-degree triangle. Now, then, once we found our point of concurrency, we just join up this. We know the force has to act through this fulcrum. So this force is going to go through here. Now for this side, now I would never ever ever do this in reality, but some students, you know, they worry that they don't understand what's going on, so I try to use different examples. I could say in this case, well, the angle here is going to be equal to this triangle here is 1 meter by 3 meters. And from that, I can use that to find this angle theta. And once I have that angle theta, that's going to be equal to this reaction, that angle theta. So I actually want to find this angle. So I'm going to write that as theta. And so theta is going to equal the inverse of tan, opposite over adjacent. And if someone had a calculator, they'd be able to figure out what that angle of theta was. I think I want to keep moving quickly. But so once I find that angle, I could then use the sine rule, as I've explained in a lot of detail in other videos. I could use the sine rule to solve this question. But let's assume that you don't even want to do that. You're like, I just don't like geometry. Well, okay, you can't really solve this without any geometry. But let's assume that you don't like this three-force method that people keep talking about. I've had enough, and instead I just want to solve it. I don't feel so my green is very good. I just want to solve, all I want to do is right now is I just want to find this force. That's all I want to do. And I'm going to say this is, well, this one's further away, so it's going to be a smaller kid. So we're going to call this one B for big kid. I'm going to call this R for resultant, the thing that's holding this thing up. Now, I'm just getting a new green pen because I feel as though the green pen I'm using is not really good. Okay. We said this distance here was 1 meter and 2 meters. So how can we solve this? Well, this is the using moments to solve things. What we know is that this is 2 meters away. I want to make sure actually, this is 2 meters to the tip of that arrow. What I can do is say, well, I have two different ways of solving it. The first way, and the way that I've shown in other videos, is I could break this force. I could break this force into a vertical component and a horizontal component. And the horizontal component I'd even ignore. And the thing is, I even chose a number that would be easy to divide. I chose root 2, or 10 times root 2, to make it really easy. But I did, I don't even care, I'm not going to use that. I'm going to instead say, what I want to do is I want to find this perpendicular distance. I'm going to extend this line forever, and then I'm going to take a set square, right, well, this plastic set square will do, and then until I've now got a perpendicular distance. And once I've got this perpendicular distance, I can then measure that. Measure it like this. And I can use this measurement. Now, what would this measurement be? Well, if I know this is 2 meters and this is 45 degrees, if this is 2 meters, what's this value going to be? It's going to be, is this opposite? It is. That's the hypotenuse. So it's going to be 2 sine 45. 2 sine 45 is the same as 2 times 0. Someone please get a calculator out for me. Oh, I think I know what it's going to be. I think it's going to be 1.414 because this is not my first time doing questions involving 45-degree triangles.
So it's 1.41.
412 something maybe? That'll do. That'll do. So, 3 significant digits is sufficient. Okay, now we're going to use something called the sum of the forces, sum of the moments. What we're going to say is the turning moment of this compared to the turning moment of that. Now, when we talked about levers earlier in the year, it made total sense. If this beam is twice as long, this kid can be twice as heavy. Yeah, if this is twice as long, the kid needs to be twice as heavy in order for it to be in equilibrium, in order for the seesaw to balance. But what we said here is, this angle here is not perpendicular. If it's not perpendicular, everything flies out the window. So now we have to figure out what that perpendicular distance is. And I did that using this trigonometry over here. Now I know the perpendicular distance, now I can solve this question. Now what I can say is that the turning force of this is going to be, the turning force of this side of the beam is going to be 14.1 newtons multiplied by 1.41. Does anyone know what that will be? I'm pretty sure it's going to be 20. Is it 20? Don't leave me guessing.
19.88.
Yeah, that's 20. 20 with some rounding issues. Okay, so that's 20 Newton meters. So that's turning, is it turning the beam, is it turning the seesaw clockwise or anti-clockwise? Clockwise. Okay, so we could say it's positive, right? Because it's clockwise. This side here then has to be turning, in order to keep this thing balanced, is we're going to need 20 Newton meters anti-clockwise. So this is going to have to equal 20 Newton meters anti-clockwise. And the distance is 1 meter. So what's the force B going to, so 20 equals force times distance. Force of B times the distance of 1. Now it's a pretty tough equation, but let's see if we can figure it out. We're going to say, well, to get this side over here, we have to divide both sides by B. So, both sides by 1. So B is going to equal 20 divided by 1, which is going to equal 20 Newton meters. So, that's the effect of what we need to do to balance it. This is some of the moments. I've gone into this in a lot of detail in other recordings. This is the level that I would expect people to know for the mid-course review for the test in the at the start of year 11. This is the level that I would expect people to understand. You don't have to use this perpendicular distance method. What most people do is they could break this down instead into 10 and 10. But if you broke it down into 10 and 10, that would work as well. Okay, so 3-force rule, moments force. Okay, moment force couple systems. Okay, I'm going to go briefly into moment force couples. So we're done with this. Okay, if I had a tap, it's not the best tap I've ever drawn, and I said that I was using, I don't know, 10 newtons and 10 newtons to turn this tap. What would the resistance to this motion be? How big is this tap going to be? Let's say it's, let's say that distance is 25 millimeters. Yeah? Well, if we took the forces, the turning force around this point, what's it going to be? If we took the force times perpendicular distance, it's going to be force times distance is moment equals force times distance equals
250 millimeters.
Oh, together they are, but this side here, just look at this force for the moment. Yeah, 125. Okay, so this is going to be 125, and that's going clockwise. What about this side? Excellent, and it's also going clockwise. So there's nothing cancelling that turning. We've got two lots of... How much total clockwise have we got? The total is we've got 250 Newton meters. Okay, now it's not Newton meters, it's Newton millimeters, because we're using millimeters. It's just important that you check that. Okay, so if we've got 250 Newton millimeters clockwise, that means for this tap to not be turning yet. If we just said, remember we said that we always look at things in equilibrium? At the exact moment, right, Jenny's going to turn the tap on, and just at the exact moment before the tap starts to turn, she applies 10 newtons on both sides of the handle. what is the resistance to turning? What is the resistance to turning? It's going to be anti-clockwise, the resistance to turning. It is 250 Newton millimeters anti-clockwise. Yeah. Now, so we could call that, we need a terminology for that. Sometimes we use RM, but in the textbook we only use MC. We call that a moment couple. Yeah, so it says the resistance to that turning is going to be 250 Newton millimeters. Now, what is interesting is that Copeland says, first of all, you don't need to break it in half and do, by breaking it in half and multiplying by 2, it would be exactly the same as if we just simply said one lot. If we just said one lot of 25, which is exactly what a student said to begin with. Maybe she's been looking ahead. One lot of force of 10 multiplied by distance of 250 equals the same. Yeah, that also equals. So just to save yourself time, instead of multiplying both forces, you can just multiply one force. Now, Copeland then says, look, he really likes SI units. He doesn't like 250, I made a mistake. Hopefully no one noticed. On the video, nobody noticed. Okay. How do you convert 25 millimeters into meters? You can divide by 1,000, that'll give you an answer. But a lot of people don't divide by 1,000. And what a lot of people do is they just put a decimal place in front of it. That is wrong, right? If you do chemistry, this is also another trap that gets you when you're doing titrations. A lot of people say 25 milliliters, and instead of saying 25 milliliters, they write 250 milliliters. This is 250 millimeters. It's a quarter of a meter. So you've got to remember to have that extra zero. Yeah? So it's important to have that extra zero. We good? Okay, so in that case, it would be 10 times 0.025, which is equal to 0.25 Newton meters. That's the same as that. Yeah? Just a different terminology. Okay, now that we've said that, the last thing we're going to say is the equilibrium of concurrent coplanar forces. So, there is more that we can do with couples. This is the level I want you to know for the examination, right? For the, not an examination, we don't do examinations anymore. The mid-course review, which is a short test. Okay. The last thing we're going to look at, and we've kind of jumped around this whole idea, and it's funny that it has the last dot point because it kind of doesn't make sense to be at the last dot point. If I have a whole bunch of forces, let's say if I had someone who walked 1 kilometre northeast and 1 kilometre southeast, and then 1 kilometre southwest, how far are they this time from where they started? Well, it probably makes sense intuitively that they're now 1 kilometre, the resultant from where we started to where we finished. From start to finish, the resultant is going to be 1 kilometre southeast. Yeah, that makes sense. And the equilibrium would be the opposite direction. But it's hard to prove that. It's hard to prove that. So to prove that, what we can do, I like to box these things into. Maybe that's the one that wasn't working very well, hopefully. I like to take the rectangular coordinates and say, well, if we walked 1 kilometre northeast, that means we went 0.707 north and 0.707 east. And then we went again 0.707 east again, and then down 0.707, and then down 0.707. And when we're doing the calculation, well then we can just look at, well, what's the missing amount? What part is missing for our calculation? We can say, well, this missing amount here, I really would like another colour. Have another colour, don't worry everybody. What's this missing amount? How much north are we missing?
0.7.
Yeah, 0.707. And how much east are we missing?
0.707.
So what we've effectively said is that we said the sum of the vertical, or in our case north, forces. So when we say some of the vertical forces, some of the x direction, some of the y direction. In this case, we're going to say the y direction is north. And the sum of the forces in the y direction, well, we're short. They help us to say that if that's to be equal, right? If we wanted to find the equilibrium, let's imagine we want to find the equilibrium. We want to find the equilibrium. The equilibrium, the missing force that we need here to get back home is we're missing 0.707. And how much east are we missing to get back home? Again, 0.707. So how do we figure that out? Well, we did the sum of the forces in the east direction. We said we've walked 1.4 kilometers east, and we've only walked back 0.707 west. So how much we have to go in order to have equilibrium, in order to be back where we started, we're going to have to go an extra 0.707. So we represent this with the formulas. This side here, the upward part of this story, in our case north, is written as this. I get sloppy sometimes when I write my sigmas, and I just write that. That's a sigma. But if you look at the formula sheet, they write this big, giant sigma. And they say the sum of the forces in the y direction equals 0. So that's your north and south. And then, I'm not going to do it as big as that last, because that was being a bit silly. Sum of the x forces equals 0. Right? That's the, in our case, east and west. And then finally, the sum of the moments about any point equals 0. Now, I've already recorded lots of videos where I prove that it doesn't matter where you take moments from. It doesn't matter if you use the fulcrum, or if you use the end of the tap, or the middle, the quarter of the tap. It doesn't matter where you go. The sum of the moments for something in equilibrium is going to equal 0. I've gone into a lot of detail on that in other videos. I don't want to go into it now. But when we talk about the equilibrium of concurrent coplanar forces, or even the equilibrium of parallel concurrent the parallel coplanar forces, we can follow these three rules. Will get us out of trouble. No protractors needed. Right? Those three rules will solve everything we do through to the HSC without using a protractor. We can just use sum of these three forces. If you use those rules, we can solve a lot of things just by saying the vertical and horizontal component. But with things like seesaws, which we saw earlier, right? With seesaws, or levers is a better term for that. Well, we need this third one here to solve some things for us. To solve when we have two unknowns. And often we will be given two unknowns. So when we have two unknowns, moments are the tool that help us to solve the questions with two unknowns. Because we can make something multiply equal 0, we can measure something, and from reference point, whatever reference point we choose, I'm going to use A. Right? It doesn't matter what reference point I choose. If I measure things from the reference point, it multiplies by 0, because force times. We have to know what moments are. Moments equal force times perpendicular distance. And so if we add up all the moments from whatever reference point we measure, everything will be 0 if the thing is in equilibrium. That was a lot of content. I've gone into everything I've just said there in way more detail than other places, but it's nice to have one big place to say, hey, here's where I've given an overview over everything.